The following question reads that sulfur is an important element and explain how burning fossil fuels contain sulfur leads to the formation of acid rain. So, in this question, we have to give a stepwise explanation of how acid rains is formed. Now, the step one, the first part is that you burn fossil fuels that contain sulfur. So, when you burn fossil fuels, what happens is that sulfur reacts with oxygen and ends up forming SO2, sulfur dioxide gas. The next part is that the SO2 formed gets oxidized in the atmosphere, and it gets oxidized by another pollutant, which is nitrogen oxide, and they end up forming SO3, and NO is produced. The last step is that SO3 mixes, it's an acidic gas, mixes with rain, and you can write an equation showing that SO3 mixes with H2O, ends up forming H2SO4, which is now known as acid rain. So the water molecule mixes with SO3, ends up producing H2SO4. Now, part B of the question reads that sulfuric acid is manufactured by the contact process, and one step in the contact process involves a reversible reaction in which sulfur trioxide is formed. Now, write a chemical equation for this reversible reaction, including the correct symbol to show that the reaction is reversible. So we need to show that. Remember, in the contact process, when sulfur dioxide is converted to sulfur trioxide, the reaction is that you reacted with oxygen, and this is a reversible reaction, and SO3 is formed. So this is the balanced equation, and all of them are going to be, they're all going to be gases. And the next question is part 2. State the conditions and name the catalyst used in this reversible reaction. So for this reaction, converting SO2 to SO3, the temperature used is 450 degrees centigrade. The pressure used is 2 to 3 atmosphere pressure, not a lot of pressure. And the catalyst that's used is V2O5, or we can name this as vanadium pentaoxide. So that is the catalyst that is used in this particular reaction. And then you have the third part. Once SO3 is formed, remember the previous step, SO3 has been formed. Describe how the sulfur trioxide formed is converted into sulfuric acid in the next steps of the contact process. So once SO3 is formed, that SO3 is mixed with concentrated H2SO4, and it ends up forming oleum, which is H2S2O7. And once you have oleum, this oleum is then diluted, H2S2O7. H2S2O7 is diluted, water is added, further water is added, and you get 2 molecules of H2SO4. So this is how SO3 is converted into sulfuric acid. SO3 is not directly mixed with water because the reaction is explosive. So instead, concentrated sulfuric acid is first used to dissolve and form oleum. Oleum is then diluted with water to form sulfuric acid. Now moving to part C of the question, dilute sulfuric acid is used to make salts known as sulfates. A method consisting of 3 steps is used to make zinc sulfate from zinc carbonate. So zinc carbonate is converted to zinc sulfate, and the steps are given. An excess of zinc carbonate is added to 20 cm cube or 0.4 mole per decimeter cube dilute sulfuric acid until the reaction is complete, and then the mixture is filtered, and you heat the filtrate until a solution forms, and then allow it to crystallize. So part 1 now states, name the suitable piece of apparatus for measuring 20 cm cube of dilute sulfuric acid in step 1. So we need to measure 20 cm cube. So measuring cylinder would be used to measure 20 cm cube. And then you have, in the next part, you have state 2 observations, which would show that the reaction is complete in step 1. Let me first, before answering this question, let me first describe what's happening Zinc carbonate is solid, so it's probably be in the form of a of powdered zinc carbonate, or it could be a solid lump. So zinc carbonate is added to it's added to sulfuric acid, which is H2SO4, and it is aqueous. Now I've written the reaction as well over here. Zinc carbonate, carbonates react with acids to produce salt, water, and CO2. So as soon as you mix the two substances, zinc sulfate would be produced, which is soluble. So you'll have zinc sulfate being produced, which would be in aqueous state. It would become part of the solution, and these carbon dioxide bubbles are also producing. So you would start noticing these bubbles. CO2 gas would also be produced as one of the products. Plus, there's going to be H2O, which would also become part of the solution. Now, what's happening is you add excess of zinc carbonate. The reason you add excess of zinc carbonate is, and if you add more zinc carbonate, if you keep adding zinc carbonate, eventually what would happen is that you'll run out of sulfuric acid. All the sulfuric acid would get used up. It's going to form these products. Zinc sulfate, carbon dioxide, and water molecules would be produced. So if you keep on adding zinc carbonate, one indication would be that the reaction would stop. If you keep on adding excess zinc carbonate, all the sulfuric acid gets used up, this reaction stops, and no more bubbles of carbon dioxide would be seen. The other indication would be that if you keep on adding zinc carbonate and all the sulfuric acid gets used up, the zinc carbonate remains at the bottom of the solution undissolved. No more further reaction is going to take place. So here I've written the two things: no more effervescence of carbon dioxide, no more bubbles seen, and the extra zinc carbonate that you're adding would remain undissolved at the bottom. No more reaction would take place with that zinc carbonate. Now moving to the other part now is, why is it important to add an excess of zinc carbonate in step 1? So the reason why you need to add more zinc carbonate is so that your solution, all the sulfuric acid, your other reactant, it completely gets used up. It finishes. So to remove the other reactant from the solution, or to get rid of H2SO4. So the answer is so that all H2SO4 aqueous gets used up. Next part is, what is meant by the term saturated solution in step 3? Now, a saturated solution is one where it can no longer hold more solute. So it's a solution that cannot hold more solute particles. That is the maximum amount of solute that can dissolve in a particular solution. Let's move to the next part. The next part is that the equation for the reaction is shown. We've already written that equation. Complete the equation by inserting the state symbol for zinc sulfate. Now remember zinc sulfate. If you remember the solubility of sulfates, all compounds having SO4 minus 2, they are considered soluble, except a few exceptions are barium sulfate, lead sulfate, silver sulfate, strontium sulfate, and to some extent calcium sulfate. So apart from these 4-5 compounds, all the other sulfates, they're going to be soluble. So the symbol that is going to go over there is going to be aqueous. It's going to be soluble. Now, part 6 is talking about name another zinc compound which could be used to make zinc sulfate from dilute sulfuric acid using this method. Now, remember, we're using sulfuric acid. Sulfuric acid or acids can react with metals to produce the same salt. So we can think of zinc metal. Zinc metal would react with acids in the same way, sulfuric acid, and produce zinc sulfate. Acids can also react with bases to produce the same salt. Bases are metal oxides or metal hydroxide, so you can talk about zinc oxide, or you can talk about zinc hydroxide. And in this question, the third compound that is used for producing salts is carbonates, which we've already discussed previously. Carbonates can also be used. But what I'm going to do is I'm going to remove zinc from the options, because the question was specifically talking about zinc compound, not zinc itself. So although zinc can be used, but it's not a compound, so we're going to go with zinc oxide and zinc hydroxide. Next part is, suggest why this method would not work to make barium sulfate from barium carbonate and dilute sulfuric acid. The reason why this method would not work is barium carbonate is going to be, so barium carbonate is insoluble. So barium carbonate is insoluble, and the reason why this method would not work is that if you take a beaker and repeat the same process, for example, this is barium carbonate, which is insoluble barium carbonate, and I mix it in H2SO4. Now, when these two mix and react, the barium compound that would be produced, the reaction is going to be barium carbonate plus sulfuric acid. It's going to produce barium sulfate plus it's going to produce H2O and it's going to produce carbon dioxide in exactly the same way. But the problem is barium sulfate is insoluble. So if I keep on adding barium carbonate, all the sulfuric acid would react and you will be left with barium sulfate. But the problem would be that barium sulfate that would be produced is also insoluble. It's a solid. So my two solids, my reactant, which was barium carbonate, and my product, which is barium sulfate that is being produced, they are both going to mix. And what basically happens is that the barium carbonate would get a coating of barium sulfate and it would stop reacting. So the reaction would not be able to produce, because as soon as barium carbonate starts reacting, there would be a surface coating of barium sulfate formed, and barium sulfate is insoluble. So it's going to block the barium carbonate from reacting further. So actually the proper answer to this question should be that the problem is with barium sulfate, the salt produced is insoluble. So you should mention barium sulfate is insoluble, which is why this reaction is not going to happen, or it would stop immediately as the reaction starts, because all the barium carbonate that you're adding, the solid barium carbonate that you're adding, would not be able to react because it's going to get a coating of barium sulfate immediately as the reaction starts. In the next part, the question now reads that in a titration, a student added 25 cm cube or 0.2 mole per dm cube aqueous sodium hydroxide. So I'm going to underline this. I have the volume and the concentration of aqueous NaOH. So I'm going to write it over here. The volume is 25 centimeter cube, and the concentration that's given is 0.2 mole per decimeter cube. So the concentration given is, let's write it over here, 0.2 mole per decimeter cube. So that's given. And it then says the student who then added a few drops of methyl orange to the solution in the conical flask. Dilute sulfuric acid was then added from a burette to the conical flask. The volume of the dilute sulfuric acid needed to neutralize the aqueous sodium hydroxide was 20 cm cube. So that basically means that this NaOH reacted with 20 cm cube of sulfuric acid. So the volume of sulfuric acid is known. It's 25. It's actually 20 cm cube sulfuric acid was needed. So that's known. Now the first part is, what was the color of the methyl orange in the aqueous NaOH? What's happening is you have a flask, and that flask contains NaOH, and you are adding sulfuric acid from the top. So H2SO4 is being added from the top. So methyl orange is added to NaOH. Remember, methyl orange has a yellow color in alkaline solution. So initially, if you add methyl orange to NaOH, it's going to be yellow in color. And as you start adding sulfuric acid, when sulfuric acid goes in excess, when you add too much of sulfuric acid, the solution would become acidic and the methyl orange would turn into red-orange color. Now the second part is determine the concentration of dilute sulfuric acid in grams per dm cube. So you're given the steps. The first thing is you have to calculate the number of moles of NaOH added to the conical flask. The way you're going to do that is, we know that moles is equal to concentration multiplied by volume, and the volume must be in dm cube, in decimeter cube. So I'm given the volume and the concentration of NaOH, and that's what I'm going to do. It's going to be 0.2, which is the concentration, multiplied by the volume, which is 25 cm cube, but that should be divided by 1000, so that it is in dm cube, in decimeter cube. And the answer is 5 into 10 raised to the power minus 3 moles. The better answer would actually be, let's rub this 5, it's supposed to be 5.00. Remember to use the correct significant figures, because if you look at the question, you would notice that all the values are given up to 3 significant figures. That shows you accuracy. 20.0 means that you are accurate up to this first decimal place or the third significant figure. All the other values are also given up to three significant figures. That's 1, 2, and third. That means you're accurate up to the third significant figure. Concentration is also given up to three significant figures. It's not zero point 0.2, it's 0.2 followed by two zeros. That means you're accurate up to this point. Beyond this point, the accuracy is not, you're uncertain. So the answer is going to be 5 into 10 to the minus 3 moles. Now we need to calculate the number of moles of sulfuric acid added from the burette. Now look at the equation now. The equation is, if you look at the equation, NaOH and H2SO4 have the ratio in which they react is 2:1. So NaOH and H2SO4, the ratio in which the two are reacting is 2:1. Now over here, I have already found the moles of NaOH. So it's 5 into 10 raised to the power minus 3 moles. So according to this ratio, the amount of H2SO4 that would react with it is going to be half. You can use crisscross unitary method, or it's very clear. If 2 react with 1, that means the amount of H2SO4 is going to be half the amount of NaOH. So it's going to be 2.5, and again make it up to three significant figures into 10 raised to the power minus 3 moles. So that's the amount of sulfuric acid that would be used. And now we have to find the concentration of the dilute sulfuric acid in mole per decimeter cube. Concentration formula is moles divided by volume, and the volume must be in decimeter cube. So the moles are already given. It's 2.50 into times 10 to the power minus 3. Those moles are already provided. I'm going to divide it by the volume. Remember, the volume of sulfuric acid that was used in the reaction was 20 cm cube, given over here. So it was 20 cm cube. So let's go back. We know the amount of volume that was used in the reaction. It's 20 cm cube, but it should be divided by 1000 so that it's in dm cube. And the answer that I'm going to get is going to be 0.125 mole per decimeter cube. Now, the last part wants us to calculate the concentration of the dilute sulfuric acid in grams per dm cube. We have already found it in mole per decimeter cube. What that basically means is that you have 0.125 moles in how many dm cube? In 1 dm cube. That is what is meant by mole per decimeter cube. So in grams per decimeter cube, what I just need to do is I need to convert these moles into mass. And the way I can convert moles into mass is I'm going to multiply this by the MR. And the MR of sulfuric acid, which is H2SO4, the MR of H2SO4 is going to be, you have 4 oxygens, so that's 16 into 4, that's 64, plus 1 sulfur, that's 32, that's 64 plus 32 is 96, plus 2 hydrogens, hydrogen is 1, so it's 98. So what I'm going to do is I'm going to multiply 0.125 moles by the MR of sulfuric acid, which is 98. So this would be the mass in grams. This would give me the mass in grams per decimeter cube. So the answer to this is going to be, it's going to come out to be 12.25 grams per decimeter cube. So this is the amount of sulfuric acid, or the concentration of sulfuric acid in grams per decimeter cube. In the next part, part E, you're given that iron 2 sulfate decomposes when heated strongly. So there is iron 2 sulfate, FeSO4, it's decomposing. And the mass of iron sulfate is given, which is 15.2 grams was heated. And it ended up forming 4.8 grams of Fe2O3. So the mass of Fe2O3 is given, and the mass of FeSO4 is given. Remember, this is probably the actual mass, the experimental mass. Actual, or you can call it the experimental mass. We are supposed to calculate the percentage yield. So I'm going to start off with FeSO4, and I'm going to first find out the theoretical amount of what amount of Fe2O3 should be prepared, should be formed according to our calculations. The first thing would be, I'm going to find the moles of FeSO4. Moles is mass divided by MR. The mass is already given, it's 15.2 grams, so it's mass 15.20 grams divided by the MR of FeSO4, which is also provided, it's 152. And the answer on my calculator comes out to be equal to 0.1 moles. So I have 0.1 moles of FeSO4. Now the ratio of Fe2O3 to FeSO4 to Fe2O3 is 2:1. So two react and produce 1. So 0.1 moles, according to this ratio, the amount of Fe2O3, the theoretical moles of Fe2O3 are going to be half that amount. So it's going to be moles of Fe2O3. The theoretical moles are going to be 0.1 moles divided by 2, which should come out to be equal to 0.05 moles. So the ratio is 2 FeSO4 produce 1 Fe2O3. So that's the amount of Fe2O3 should be produced as half the moles of FeSO4. So it's going to come out to be 0.05 moles. Now move to the next part. We found the moles, the theoretical moles of Fe2O3. I'm going to find the mass of Fe2O3. That would be moles multiplied by the MR. Moles are 0.05. The MR is probably given over here. It's given as, if you look over here, it's given as 160. So the answer is going to come out to be, it's equal to 800 grams. So that's my theoretical mass, Fe2O3. That's the theoretical mass. What I did was I found the moles of FeSO4, which came out to be 0.1 moles, and according to this ratio, the amount of Fe2O3 should be 0.05 moles. And then I multiplied it by the MR, and I found out that 8 grams should be produced. Now, in the actual experiment, you're getting 4.8 grams. So the output is, the reason you're getting lesser is that in the actual experiment, there's a lot of impurities, the reaction conditions are not suitable, so the reaction generally doesn't tend to complete or doesn't go to completion, or there are lots of impurities, so a lot of the sample is not pure enough to get the complete yield. So theoretically, we should be getting 8 grams, but you're only getting 4.8 grams. So the formula of yield is going to be, yield is actual divided by the theoretical value that you obtained multiplied by 100, and in our case the actual came out to be 4.8 grams, the theoretical came out to be 8 grams, and I'm going to multiply it by 100 to get the yield, which is going to come out to be equal to 60%. So this over here is going to be the yield of the reaction. Actual was 4.8 grams, theoretical was 8 grams. So the percentage output is that 100% yield is when the theoretical calculation and the actual calculation are exactly the same. But since you're getting lesser, it's 4.8. You should be getting 8 grams. So 4.8 divided by 8 into 100, so that's 60%. So the calculation that you did, the actual output is only 60%. So 60% is the answer to this question.